The next thing that we want to look at is the three laws of thermodynamics. We'll start with the first law of thermodynamics. And what that says is that when heat enters or leaves a system, the system gains or loses an amount of energy equal to the amount of heat transferred. The first law of thermodynamics is a consequence of the law of conservation of energy. Now, remember what the law of conservation of energy is. It says that the total energy in a system remains constant. If you can find where all the energy goes and you add them up before and after something happens, the total is going to be the same. And so you might remember, for example, we looked at an example of something falling, and we said it has a potential energy mgh. And as it fell, the h got lower, the height got lower, so it was losing potential energy, but as it fell, it started picking up speed, and it would start going faster and faster, and it would gain 1/2 mv squared. And so the potential energy would be converted into kinetic energy. Halfway there, it would be half potential and half kinetic, and at the bottom, it would be all kinetic. And so this was an idea of conservation of energy. Well, heat is a transfer of thermal energy. And so what the first law of thermodynamics says is that the law of conservation of energy still works. I've got heat energy flowing from one body to another body. Well, the total energy of the system before and after that happens has to be the same. So what happens when you add heat to a system? Well, the first law of thermodynamics goes on to tell us that when heat is added to a specific system, that could be a steam engine, that could be the Earth's atmosphere, that could be a living creature, whatever your system is, you've got heat going into it. That heat can do two things. It can serve one of two possible effects. One is it can increase the thermal energy of the system, or two, it can enable the system to do work on its surroundings. And it actually can do both at the same time, but those are the two things it can do. It can increase the thermal energy, or it can do work. And so this is a way that we can express the first law of thermodynamics as an equation. The equation tells us that the heat added to a system equals the increase in the system's energy, specifically its thermal energy, plus the external work done by the system. That is the first law of thermodynamics. Now, the second law of thermodynamics says that as energy is transferred or transformed, more and more of it is wasted. Basically, the first law of thermodynamics says that you can only get out of a system what you put into it. If I put heat into a system, all I can get out of that is what I put in. But the second law of thermodynamics tells us that you can't even get that much out, that some of the processes is going to waste the heat in a way that can't be converted into work. And so you can't get, if I put heat into the system, I'm going to increase its thermal energy, I'm going to enable it to do work on its surroundings, but I can't convert 100% of the heat I put in into work. And so some of the heat that I put in the system is going to end up being wasted. That's what the second law of thermodynamics tells us. And as a consequence of the second law of thermodynamics, and sometimes this is another way to say it, heat never flows spontaneously from a cold object to a hot object. It's always the other way around. So if I have two objects, one of them is hot, the other is cold. Now, what does that mean, that something is hot compared to something that's cold? It means it has a higher temperature, right? So this guy is going to have a higher temperature, and this guy is going to have a lower temperature. And what that says, if you put these guys in contact with each other or near each other where they can exchange energy, the heat is always going to flow from the hot to the cold. It's never going to go the other way, unless you do work on the system. That's how a refrigerator works. A refrigerator takes the heat from inside the box of your refrigerator and dumps it outside the box of the refrigerator. And it does it by, you have electricity which goes into the refrigerator, and there's compressors and other things that are doing work, and that enables the temperature to be lowered inside the refrigerator, you're actually making the heat flow from a colder object inside the refrigerator to a warmer object, the air outside the refrigerator, but you're doing that by doing work. If you're not doing work, if you're not doing external work on the system, you just have two things of different temperature and let them go, this rule is going to apply. The heat is always going to go from hot to cold. The third law of thermodynamics is one that is not as important as the other two, but I've included it for completeness. And it basically says one can never reach a temperature of absolute zero. And we've talked about this previously. If I'm doing an experiment and I'm trying to get something colder and colder, it's in a surrounding that's going to be at a higher temperature. And so as I get this colder and colder and colder, what's going to happen? Heat is going to flow from the higher temperature surrounding into my experiment and warm it up. And so it sort of defeats my experiment. I can never get all the way to absolute zero, but I can get very, very close. Now, let's go back and think about the second law of thermodynamics, because there's yet another way that people think about it and talk about it. What they say is that the second law of thermodynamics requires that the entropy of a system will always spontaneously increase, or at best remain the same. It never spontaneously decreases. Now, what is entropy? Entropy is a measure of the disorder of a system. And so imagine you have a box here, and the box has a gas. And so these blue dots are representing the molecules of the gas. Now, if I were able to get a pump and suck all the air into a corner, so here's all the air in the corner, and I let it go, it's gonna, these guys are gonna spread out. They're gonna become more disordered. You're never gonna have a room filled with gas and have all the gas molecules just migrate into the corner. I'd have to pump them there or do something to get them over there. I have to do work on them, force times distance. I have to physically move them over there. They're never just spontaneously going to decrease their positions and move over to that corner. But if I put them in the corner and let them go, we know they're not going to stay there. They're going to spread out because the disorder of a system, its entropy, will always spontaneously increase. Now, if you do work on it, you can make it decrease, but you can't just be watching it and have it spontaneously decrease on its own. It'll never happen. And so you can see here this pile of bricks here. If you tossed a bunch of bricks off of a truck, what kind of pile would you more likely produce? One that's very ordered, or one that's kind of disordered and all helter-skelter? Well, I think you would guess that this is a much more likely scenario. That's because the entropy of the bricks is going to want to increase over time.